DeepSeek, an AI lab from China, just dropped a new paper, and honestly, this might be the most important AI paper of 2026. They fixed a core architectural problem in transformers using a math from 1960s. In today's transformers, every layer has two main parts: attention and feed-forward network. After each of these, we use something called residual connection, which means we add the exact input back. Why do we do this? Because as neural network gets deeper, information doesn't always flow smoothly. Without residual connections, signals can fade away or blow up as they pass through layer after layer, just like this green ball here, which shrinks until it disappears. Residual connections make sure information doesn't get lost, even after hundreds of layers. But residual connections come with a hidden problem. They always add the same input with the same strength at every layer. This makes early information dominant. Even when deeper layers learn better features, the old ones keep getting added again and again. So residuals prevent information loss, but they also limit feature transformation. This rigid addition becomes a bottleneck. The model wants to decide what to keep, what to reduce, what to amplify. And residual connections don't allow much flexibility. So researchers tried something else. Instead of one residual path, they divided input vector into many small paths. This is called hyper-connections. Instead of adding the input just once, the model divides it into multiple streams and uses a learned mixing matrix to blend and redistribute information between the streams. This caused a disaster. Signals exploded, training became unstable, and models collapsed. DeepSeek realized something very simple and very powerful. The problem wasn't multiple paths, it was uncontrolled mixing. This mixing decides how much information flows from each stream to every other stream. This is where DeepSeek used a math from 1960s called Sinkhorn normalization. Now let's look at the proposed approach of forcing mixing matrix to behave like a perfect redistribution. This is done using Sinkhorn normalization process, which rescales each row so the row sums to 1. Then it rescales each column so the column also sums to 1. Because of this nature, this matrix is also called double stochastic matrix. This guarantees something very important. No signal is amplified, no signal disappears, information is redistributed, not multiplied, and every layer moves information around, but the total signal is preserved. This is called mHC, Manifold-Constrained Hyper-Connections. mHC keeps residual connections stable across multiple paths, reducing their weaknesses. DeepSeek's approach isn't about making models bigger, it's about making information flow better. And that simple shift could make large language models much more reliable.